Hello, everybody. So 2 videos ago, we talked about the pumping lemma. The pumping lemma was a way to demonstrate that the language is not regular. So it showed the limitations of DFA, languages that cannot be recognized by a DFA. And today we're going to see the Myhill Nerpde theorem, which is another way of demonstrating the limitation of DFAs, and in a sense stronger because it gives a characterization of regular languages. In other words, every language that is not regular, we can demonstrate it with the Myhill Nerpde theorem. And similarly, every language that is regular, we can also demonstrate it with the Myhill Nerpde theorem. We'll see some similarities between the definitions that we are using here and the definitions we used in the previous video to show DFA minimizations. And in a sense, this is the flip coin here. So the limitation of DFAs, the fact that they are limited, primitive in some sense, is also the reason for which we can work with them quite nicely. So we can do things that we cannot do with more sophisticated models of computation. This is one reason they are so popular in areas like verification. So let's dive in. And we'll see definitions that are a little bit similar, but they're different. So take care to see the subtleties here in the differences. So in DFA minimization, we defined an equivalence relation between states. Here we're going to define equivalence relation over strings, so between strings, and with respect to languages. And this will mean that we can apply this for any language, not just regular languages. So let L be some language, and X and Y are two strings. We will say that X is L equivalent to Y if for every Z, XZ is in L if and only if YZ is in L. In other words, if you were to read, if I tell you that the prefix that I just read is either X or Y, and the suffix is Z, then you don't care if it was X or Y, if your purpose is to decide membership in L. Define X and Y to be indistinguishable to L if X is L equivalent to Y. So this language doesn't really distinguish them, doesn't care, doesn't separate them. And one claim is that this is an equivalence relation. It's not hard to show it. It's very, very similar to showing the equivalence relation that we did in the DFA minimization. A string is definitely equivalent to itself. X is equivalent to Y if and only if Y is equivalent to X. The definition here is completely symmetric. And the one that's a little bit more subtle is that X is equivalent to Y and Y is equivalent to Z, then X is equivalent to Z. And the proof is just like we had in the last video. Now, what does it mean that we defined here an equivalence relation? It means that we can now talk about equivalent classes. We can divide all the strings in the world to equivalent classes, and there could be infinite number of equivalent classes for some languages and finite number of equivalent classes for other languages. The Myhill Nerpde theorem says that this distinction is exactly the distinction that tells us if a language is regular or not. So the Myhill Nerpde theorem says that a language L is regular if and only if the number of equivalence classes of L is finite. So if L divides the world all the strings into finite number of equivalent classes, then this is a regular language. And if it divides it to infinite number of classes, then it is not a regular language. Let's prove this theorem, and we'll start by showing the if. So if L is regular, then the number of equivalent classes is finite. If L is regular, then there exists some DFA for L. Let's say that it's M. And we're going to define the relation X is M equivalent to Y. If reading X or reading Y from the start vertex leads to this, from the start state leads to the same state. So the DFA after reading X or reading Y reaches the same state, and therefore it doesn't know which state it is. The claim is that first, this is an equivalence relation. That's again very similar to the previous proof of equivalence relation. And more trivially, that it has at most Q classes, right? Every string that is read reaches one of Q states, the size of Q states, and therefore it falls into at most one of these Q classes. We can divide the classes by the state you reach, the machine reaches after reading it. Why am I saying that there are at most Q classes and not exactly Q classes? Because there may be states that are unreachable. So therefore, there will be no string that reaches them. If X, another claim is that if X is M equivalent to Y, it is also L equivalent to Y. This is also not hard to show. If X is M equivalent to Y, it means that for all Z, XZ and YZ reach the same state of M. Why is it true? After reading X or Y, you reach the same state, and now you read Z. So you don't remember if you read X or Y. The machine doesn't remember if it read X or Y because it reached the same state. And now reading Z will reach the same state. So XZ is in L if and only if Y is in L, and therefore X is L equivalent to Y. So the corollary is that the number of equivalence classes in L is at most the number of equivalent classes in M, and this is the size of Q, which is finite. So we prove that if L is regular, then the number of L equivalent classes is finite. Let's show the other direction. So if the number of classes, equivalent classes is K, we want to show that there is a DFA for L with K states. That is to build the DFA using these equivalent classes. So the states of the DFA would correspond directly to the equivalent classes of L. Define the DFA M, where Q is the set of equivalence classes of L. Q0 is the equivalent class of the empty string. So every string Y, which is L equivalent to the empty string. And that's nice that we're going to start with the empty string, right? It's like reading nothing. The transition function delta of the equivalent class of X that reads sigma gets to the equivalent class of X sigma. The finite states, the accept states, are all the equivalent classes of X where X is in L, right? You do want to accept these strings. And the claim is that M accepts X if and only if X is in L. And yeah, so I won't prove that, but the proof is not very hard, especially given things we've gone through in the last video. So let's talk about using the Myhill-Nerpde theorem. It gives us a new way to prove that the language is not regular. So L is not regular if and only if there are infinitely many equivalence classes of L. And this means that L is not regular if and only if there is a set of a sequence of infinitely many strings, W1, W2, W3, and so on, such that for all Wi different than Wj, or actually for every I different than j, we'll have that Wi and Wj are distinguishable to L. So there is a Z that exactly one of Wiz and Wjz is in L. So this means that each one of these Wi's is in a different equivalent class than all the other Wi's in this sequence. And we demonstrated that there are infinite many equivalent classes. Perhaps we're not representing all of them, but it doesn't matter. We already represented infinite number of equivalence classes. We'll call this kind of set the distinguishing set, or a distinguishing set for the language L. So let's see an example. See our favorite language that is not regular. So 0 to the n, 1 to the n. That's all strings that start with zeros, end with ones, and they have the same number of zeros and ones. Consider the infinite set of strings 0, 0, 0, 0, 0, 0. So the ith strings as I zeros. And take any pair 0 to the m and 0 to the n of distinct strings in S, and we want to show that they are distinguishable to L. And the string that will distinguish them is Z, which is 1 to the m. Because 0 to the m, 1 to the m is in L, but 0 to the n, 1 to the m is not in L. So this Z distinguish them. So all pair of strings are in S are distinguishable. So hence we have infinitely many equivalence classes in L, and L is not regular. So that's the way we proved another way to prove that this language is not regular, if you didn't convince yourself with the pumping lemma. So we'll see more examples in exercises. So as a parting thought, the Myhill-Nerpde theorem is a powerful characterization of regularity. Thanks.